Recording is rolling. It is Wednesday, September 17th. Here's the top scientist for your kinematic motion quiz. So, awesome job. You made the list. Yeah, I do still have a few students who need to take quiz, so working on getting back. But after getting back, to be able to do corrections, but gotta get everybody to take that first. Okay. Yesterday, you guys did a spring scales lab. And I want to go over the ideal answers with you guys. Okay, so yeah, you guys had a lot of people. Really, it was like 10 mini labs, what it is. And I want you guys to see some fundamental principles about how forces work. That's going to be integral to everything we're doing for the next few weeks. I have a mystery cup. That was fun. And then if you guys have a notebook, we're going to start doing a bunch of free body diagrams by the end of class, and we'll do more examples tomorrow, and then eventually work with puzzles. Guys, I gave you guys some puzzles the other day. I don't have a due date on those yet. Great, they look like these. I don't have a due date on these yet, but it's going to take us a few weeks. So, and I might narrow this down too, because I know there's a lot of these puzzles from 2 chapters. So I might narrow these down over the weekend. What I want you guys to actually do, and do some of those with you guys. And so, great. There we go. Spring scales. So the first one, I wanted you guys to just hang different weights or different lab masses. So there's that whole box of these lab weights, lab masses. They can measure these in grams or kilograms, and what's the corresponding course. So I'm going to make up some. What if you had to say like 100 grams, 200 grams, 500 grams, and 1 kilogram? You guys, 1 kilogram, is that called 1,000 grams?
Yeah.
We're going to prop this up a little bit. There we go, a little better. Okay, so guys, 1 kilogram weighs about how many newtons? 10 newtons. She got like 9.8. But spring scale showed 10. That's good. Okay. Oops, sorry, that's this one right here. Oops, I messed that up. This could be 1.0 newtons, or just like 1 newtons. Okay. This should be close to 2 newtons, 5 newtons. So we got 1, 2, 5, and 10 newtons. Okay. Now, if you graph it, remember on your graph, scale these linearly, so the mass goes up to 1,000 grams or 1 kilogram. Might go like let's go 100, 200. These could be in maybe grams, I guess. I think 500, 300, 400, 500, 6, 7, 8, 9, 1,000. Like over. And the corresponding force, it could go 2, 4, 6, 8, 10 newtons. This could be in newtons. 0, 2, 4, 6, 8, 10. Okay, so 100 grams weighs about 1 newton. 200 grams about 2 newtons. 500 grams about 5 newtons. 1,000 grams weighs 10 newtons. You should have gotten a linear relationship. Pretty straightforward, I think, right? Something like that. Okay. And hey, let's make an equation out of this. Like, guys, what's the slope of this graph equal to?
1. No. 1.
It represents a physical value. It represents the gravity field of the planet. Yeah, like about 10 meters per second squared. That's exactly what that is. So as an equation, it can say F for the force equals whatever mass times this gravity field, like that. Okay. Actually, guys, mg, mass times gravity field, that's usually what it is used to represent weight anyway. So force due to gravity or weight is mg. That's all. And hey, to guide along with these posters, I'll go with the posters while we're going on. Okay. So you guys, of course, are using these spring scales, and the more force you put on the spring scale, the more it's going to stretch. Okay. More force is going to stretch more. Okay. And like this green one needs a small force to stretch, so that'd be like a small spring constant K. This gold one's really stiff, So you need a huge force to stretch a little bit. Huge force to stretch a little bit, that'd be a really steep curve and a very large K. Or in terms of restoring force, like the spring always pulls back or pushes back the opposite way, whichever displacement it has. So it's called negatives. Okay. And then here's basically your first mini lab. So 2 forces. This is the diagram you want to have in mind. Is there's weight down, spring force up, and they zero out for equilibrium. So that's all we've done so far.
The way with it.
No. Next one. What if you have 1 lab mass? Like suppose this is 1 kilogram. And you have 2 spring scales, and you sort of shift them back and forth. Now, okay, 1 kilogram, weighs how much again? 10 newtons. Okay, so let's do it. Okay. Could the split like 5 and 5? Could it be 5 newtons here and 5 newtons here? Could be. So if you go, F left is 5 newtons, and F right is also 5 newtons, and they add up to 10 newtons. Okay? 10 newtons up, balances 10 newtons down. right? But what if you shifted them a little bit so that this one only holds 3 newtons? Now this one holds how much? 7 newtons. What if you shift it again so this one only holds 1 newton? Now this one's holding how much? 9 newtons. What if you shift it again so this holds 6 newtons? Now this one's 4. But you guys see the rule is they always add up to 10 newtons up to balance the 10 newtons down. So it'd be equilibrium. Okay, so F left versus left right. Let's go 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay, so like that. Okay, so I got a point at 5, 5. That's got a point at 3, 7. It's like right. Got 1, 9. Got 6, 4. Okay. And what you should have gotten ideally is like a linear relationship with a negative slope, just like that. And it crosses at 10, 0 and 0, 10. Oh, yeah. Maybe for a 1 kilogram math, that would be true. All right, good so far. Good so far. All right, this one in 2 dimensions. Now, this one, guys, this one takes some thinking, and we might spend some time looking at this one here. So let me find this on my, get this ready to go on my posters too. Right, so I'll use my example of I got a 1 kilogram lava here. So suppose I was hanging this from got this bottom spring and I got 2 top springs. So if I had this lab weight, would this be 10 newtons for the bottom spring, regardless of what the top springs look like? Okay, so the bottom spring would always be 10 newtons. 10 newtons on the bottom spring. 10 newtons. Okay, regardless of what this angle is. And you guys see this angle is with respect to the vertical. Okay, and be symmetrical, so this would be the same angle over here with respect to the vertical. So start at 0 degrees, which matches this picture, right? This picture is the 0 degree angle. Okay? Now I'll throw some angles. Suppose you did 30 degrees from the vertical, 60 degrees from the vertical, and let's say 80 degrees from the vertical. We'll just make up some numbers. Okay, so what happens to each top spring? Right? Now, guys, as you pull these apart, let's start with the 0 degree one. Guys, if they were straight up, both vertical, and it was all symmetrical, then it would have been how much and how much? 5 and 5, so 5 newtons and 5 newtons, something like that. So each top spring could be 5 newtons, right? Again, if they're symmetrical, they should be the same number, ideally. Right? But then as you spread them out, maybe that starts to slowly change, and then the more you spread them out, maybe it changes a little faster, and you get closer to a T. Did you have to like really start pulling to make it closer to a T shape? So I think that force was increasing, right? The force being increasing. Right, you guys get that? Okay. Now, all right, everybody's looking up here. Guys, everybody's looking up here. Okay. So here's your guiding principle. This is exactly this mini lab. Okay. The guiding principle is this. All right, there are 3 forces, but all the forces have to zero out. And in fact, if you break the forces into components, like these diagonals, notice I break them into horizontal and vertical components. The components also zero out. You guys see it? Okay. So and that's with the Cartesian system that runs vertical and horizontal. Okay. Do you think in principle I could introduce any wacky Cartesian system like here, or maybe align this one, right? All the components would still zero out? They sure would, right? But maybe the gravity field could be like the vertical axis and something. Okay. So I got the weight is already aligned with the y-axis. But I've got these diagonals. I'm going to break these into components. Say how much over and how much up for each one. You guys see the right and the left cancel out, zero out that way. Okay. And if you had an angle, like guys, if you're measuring this angle right here, it's like so many degrees. So it's like 50 degrees. Would this angle here also be 50 degrees? Right. So this angle here is this angle. Do you guys see that? Right. Therefore, guys, this blue component would it be the spring force times sine or cosine of this angle right here? Sine. And what about this green component? It would be the cosine component. Actually, I'll go ahead and draw that out on paper too. Draw that here. So we got notes. I got some weight, mg. Here, I'll call that 10 newtons. Say I have that 1 kilogram lab mass weight 10 newtons. Okay. And then introduce a Cartesian system. Okay. I'll have some spring scale maybe pulling up sort of up and to the left, and another spring scale pulling sort of up and to the right. Okay. I'll call this F left and F right. Okay. So spring force left and spring force right. Okay. And then I'm going to break these into components. Okay. Well, this left one was pulling kind of to the left, but also kind of up. Okay. Notice I dash those components. You guys see I dash them? And this one on the right is pulling kind of to the right. and kind of up. Okay. And here I'm gonna, well, I'll just call it theta. Okay. And you guys said that's the same thing as that theta. Those thetas are the same. 50 degrees, 50 degrees, 60 degrees, 60 degrees. Okay. So when the side B, whatever the force on the right side is, times, you guys just told me that these sine theta because it's opposite of theta. Okay. And this would be force right times cosine theta because it's adjacent to the reference angle. Okay. Now, there's something I want you guys to see, especially from the symmetry. Like if these are the same force right equals force left. Okay. If that's true, then what do these two upper forces have to add up to? 10. Doesn't this plus this have to zero out with this, which is down 10? So down 10 here, these have to add up to 10. And if they're the same, if it's symmetrical, then each individual vertical component has to be how much exactly? 5. Doesn't this have to be 5 newtons? You guys see 5 newtons? Right, everybody see that? And this one would also be equal to 5 newtons. Okay. Notice that's regardless of what the angle is. I didn't even tell you the angle. Guys, could this angle be 30 or 40 or 50 or 60 or 70 degrees? And this is always pulling up with 5, and this is always pulling up with 5? Yeah? And the horizontal's changing and the overall's changing. Okay? But you gotta support the 10 degree weight. Okay? So the guiding principle here is that the sum of the forces in the y direction goes to 0 newtons. Therefore, 5 and 5 up balance with the 10 down. Okay. And it also works horizontally. So some of the forces in the x direction also zeroes out. Okay. And all that means is that this one pulls right as much as this one pulls left. Okay. So let's try some values here. Actually, we can kind of come up with an expression. We're going to pick up from that one right there. That one right there. We got it. So if that's true, then can I solve for the force on the right side? So therefore, the force on the right side is equal to. Can you guys see this in your notes? Can you guys solve for this force right? Got it right here. Equals what? 5 newtons divided by cosine of the angle. Wouldn't that be true? All right, you guys see that? This is equal to this. Again, divide both sides by cosine theta. You guys, let's look at the expression right here. All right, is everybody following? Okay, so what I can do is I can get toward like ideal answers here. So what if I had a 30-degree angle? Remember that before? So now 30 degrees is not too far, so I don't think the force would change too much, but maybe it goes up a little bit. So let's see how much. What's 5 divided by cosine of 30 degrees? Okay. And I'm getting 5.77. Maybe I'll call it 5.8 newtons. This is the best you could read from spring scale, or even 6. Right. So going from here to here, it went up about 5 to 6 newtons. So it went up a little bit, hardly anything. Okay.
Wouldn't it?
Well, I'm saying each angle is so this could be 30 and this could be 30, so the total angle could be 60 between them. Yeah, that'd be true. Right? Now, guys, what if I take this angle all the way to 60 degrees? And actually, before I plug that into the calculator, I want you guys to see that this is actually going to be a special case. Okay. So get my Cartesian system going. You guys are writing this in your notes. Got your notes. Okay, put the center mass dot right here. They all come together. I'll have 10 newtons down this way. 10 newtons, that's okay. My weight, my gravity force is 10 newtons. Okay. What if this angle from the vertical is exactly 60 degrees? Now, something special is going to come out of this. Okay, and then the other way also is 60 degrees. So if this is 60 degrees and this is 60 degrees, each from the vertical, I'll call this force left and force right. Okay? Now, break these into components. So this one pulls left, this one pulls right. And they both pull up a little bit. Actually, you guys know exactly how much they both pull up. Okay, guys, how much do they each pull up?
5 newtons.
Yeah, 5 newtons each. So my picture is a little wonky. Sorry about that. But this would come out to 5 newtons. And this would also come out to 5 newtons, wouldn't it? Okay, so you know that. 60 degrees is also up here. Okay. Now, guys, what's the total angle? Okay, so the total angle between these two is 120, right? What is this angle right here? 120? What is this angle right here? 120? You guys see 120, 120, 120? Which adds up to 360? Is that what I'm trying to get at, what I want you guys to see, because there's lots of different ways to approach things, see things, think about things, okay? Is that this particular setup with this angle has radial symmetry. This is the only one that has radial symmetry. And if that's true, if it's like radially symmetrical, see, like I could spin this around, and it should look identical. Hey, look, that looks the same. Hey, that looks the same. All looks the same, doesn't it? Right? What that means is, like, just visually, you can see what is this force right here. It has to be what? And what is this force right here? It has to be what? Well, this one was 10, and it's radially symmetrical. It looks the same no matter how you turn it. So this has to be 10 newtons. And this has to be also 10 newtons, specifically for an angle of 60 degrees, because it's radially symmetrical, right? Or at least that's what I'm claiming. At least that's what the picture shows. Is that what would that agree with the equation? Because we came up with an expression earlier for any angle. If I plug in 60 degrees right there, do I better get 10 newtons? Yeah, go ahead.
Since like the gravity is cooling down,
Yeah.
so like it would be still the same even though they're like equal, they're not like
Yeah, because if I take out the fact that it's weight specifically or tension, if it doesn't matter, and I just do like 10 newtons, and then I go 120 degrees, 120 degrees, and I go 10 newtons, and I go another 120 degrees, and I go 10 newtons, and then another 120 degrees brings me back to the beginning. Right? You see how it doesn't matter? Because what if we change the story completely? What if we have a three-way tug of war and we tie 3 ropes together? Right, you guys ready to go on the helicopter ride? All right, so we're up in the helicopter, looking straight down. You guys see we're looking straight down from the helicopter? You got a team of people here. Yeah. Team of people here. Yeah. Team of people here. Yeah. They're all pulling on the ropes. Yeah. This point's not really moving. You guys see that? Okay. Guys, does it matter how I turn this? Isn't the tension of the rope always going to be the same? Is there because it's radially symmetrical? You see it? Okay. Now, if I just swap out the story and make one of these a weight and two of these a tension, it's still the same diagram, right? Still the same diagram? Okay. So what I'm claiming here is if I plug in 60 degrees, I better get 10 newtons. Is that true? Right. Let's see if that actually works. Scroll up, scroll over. For the cosine, I'm going to plug in 60 degrees. Okay. Should I get 10 newtons? Boom! Exactly 10. Oh, yeah. Exactly 10. So this is 10 newtons here. Newtons. Okay. What if I keep going? What if I go to 80 degrees? Okay. Oh, whoa. That jumped way up to like 29 newtons. I'll call it 29. 29 newtons. Would that fit on the gold scale? Yeah, it would. Right? It'd be like, got to. So the gold scale will hold that, but not the green scale. The green scale only goes up to 5 newtons. Okay. So it looks like as the angle was changing, the force in each scale first went up a little bit, and then it started skyrocketing a lot. Okay. What if you try to make a perfect T? Guys, a perfect T, this angle approaches what angle? 90 degrees. What do you think would happen if I plug in 90 degrees? What is cosine of 90 degrees? 0? What's 5 divided by 0? Divided by 0, error. Not going to happen. And on a graph, that would be represented by a what? If you divide by 0, it shows up as a vertical asymptote. Let's plot these points. So I have the x-axis for you guys. That's the angle in degrees. Let's go 10, 20, 30 newtons. So 10, 20, 30, and these will be forces in newtons. So 0, 5 is a point. At 0 degrees, each spring scale is reading 5 newtons, each top spring. If I change that to 30 degrees, it drops up to almost 6 right there. Just goes up a little bit, but hardly anything. Almost not noticeable. Go up to 60 degrees. Ooh, now the spring force is doubled from the original value, from 5 to 10 newtons. Go up to 80 degrees, and now it's really skyrocketing. It's right there. Okay. And if you plug in 90 degrees, it blows up my calculator. Vertical asymptote. So doesn't that look like that right there? Okay. That's the graph I was looking for. Okay. And I'm claiming that that's represented by this expression right here. This and this are the same thing. Okay. Now, let me show you guys that's true in Desmos. Oops. How about that? Okay. So if I do if I do 5 divided by cosine of x, basically, right? Something like that. Cosine of x, or 1 over cosine, is that also called secant? Right. So this is a secant curve. You don't see too many of those, but got something like that. Right. Ah, look at that. So there's a secant. If you graph secant of x or secant of theta, this is the basic graph. Right? Now this is going to be x-axis in terms of radians. Okay, not degrees, but radians. Because 90 degrees is that same thing as pi over 2 radians? Is that 1.5 something radians? Right. So if you look at like 1.57, whatever it is, right, that is exactly where this vertical asymptote is. Look at that. It's this vertical asymptote. Right? Okay, guess that. And what we graphed was actually just this bit right here. Boink, just that bit. Okay, that's the whole thing. Okay, guys good? All right, so a lot going on there. A couple questions. As the angle approaches 90 degrees, let's say this approaches a T shape. The force in each top spring scale approaches what? Infinity. Yeah, it just keeps going up. Infinity. Okay. So can you ever make a perfect T shape? No. Because no matter what, each of these spring scales has to provide an upward component of 5 newtons, no matter what the angle is. Isn't this always 5 newtons? We established that before. Is that too? Right. And then let's go back to these posters again. Right. So this guiding principle will solve any of these truss joints. Right? Here's an asymmetrical version of the same idea. So, right. What if these angles are different? I got an alpha and a beta. Okay. But the guiding principle is the same. This one right, this one left, the same. So f left cosine alpha shows up here. And this f right cosine beta. You guys see those two subtracted, they zero out. Right? And then vertically, this up plus this up minus this down should zero out. So f left sine alpha right here. And f right sine beta right here. Add those together. Subtract off the weight. That has zero out that way. Okay? And if you have enough information, like if you knew what these forces were and you had to solve for the angles, you could do that. If you knew what the angles were, you could maybe solve for a force. Okay? So once you know so much. Actually, this is the next one. Ching ding, ching ding. So you put some weights on. What's happening to these spring scales? What we're looking at. Suppose they call us 1 kilogram, 1 kilogram, 1 kilogram. So before. Let's say spring scales themselves are negligible compared to those. Okay. What do you think the bottom scale reads? 10 newtons. How about the middle one? 20 newtons. And how about the top one? Does it have to hold everything? Which is like 30 newtons? So like 10, 20, 30? Is that? Okay. You guys know like barrel monkeys? A bunch of monkey chains. Would it be easier to be the bottom monkey where you're just holding yourself and you just hang on? Or the top monkey where you have to hold all your monkey friends? Yeah, it'd be easier to hang on the bottom, right? Or what if you walk into an old warehouse? You see this heavy metal chain, like heavy metal links, this big chain hanging from the ceiling. It's been hanging there since like 1938. They're all getting rusted over. Which link is most likely to break first? One near the one at the top. Right. Oh, slip an extra spring scale in here. I'll keep the masses the same. 1 kilogram, 1 kilogram, 1 kilogram. Okay. I think this bottom scale still reaches 10 newtons, and the top scale still reaches 30 newtons. The question is, what about the middle scales? Guys, does it go 20 and 20 or 10 and 10? 10 and 10, it splits. 10 newtons, 10 newtons. Aha. Right? That's why sometimes this string I give you is kind of thin, but if you like double it up, it makes it stronger. Yeah. Okay, this splits. All right. Ooh, let's put some motion here. Motion. So if you accelerate this up or down, and I give you guys a little note here that careful that acceleration and velocity are different concepts. So you can have one direction on velocity, and you might have the same or the opposite direction on the acceleration at the same time. Okay? So here, let's do accelerating up. And there's 2 ways to accelerate up. One way to accelerate up is maybe you start from rest and you move up faster, faster, faster. Okay? So suppose this way's gravity and this way's like up. Can you guys imagine that? Okay. Maybe you have a weight hook down here. Okay. So here's what this would look like in slow motion. So if I start from rest, okay, and then I start to accelerate up, see how this weight goes, like this is a 2 Newton weight. So if it's hanging at rest, it'd be 2 Newtons. If I start to accelerate up, see that maybe it jumps up to like 3 or 4 Newtons. Okay. And then as the elevator goes up at constant velocity, then it just goes back to 2 Newtons and hangs out at 2 Newtons. Okay. Guess that. Okay. Now, the other way to accelerate up, well, here, I'll do that later. Okay. So, if you accelerate up, doesn't the force rating go up? Is that okay? Now, how about this? Suppose this whole thing's moving upward, reading 2 newtons, 2 newtons, 2 newtons, and then you suddenly come to your destination floor at the top, and you stop. Wouldn't this alleviate? Maybe go to like 1 newton, and then jump back to 2 newtons. Right. Right. So it goes up and it jumps up a little bit. Okay. So that would be a downward acceleration. Even though the elevator is moving up, it's accelerating down, slowing to a stop. Is that kind of like a car braking to a stop? Even though the car is moving forward, it slowed down, so it has negative acceleration, sort of. Same kind of. Okay. Now the other way, let's do it the other way. Let's say you started at a top floor and we want to move down to a lower floor. When that elevator starts moving, guys, when the elevator starts at the top floor and starts moving down, is that a downward acceleration? Yeah, initially it is. And would that force rating go down a little bit? Sure would. Right? And then as it's going down at constant velocity, would that be the same as being at rest? Yep. Okay. And suppose it's come down to the destination floor and it slows down, comes to a stop. Guys, moving down, slowing to a stop. That's which direction is the acceleration? Up. And actually gains weight for a little bit, or gains apparent weight, I should say. Okay. So that would actually be back to the first category again. Okay. So okay. Here, I'll show you guys a video of exactly that process. I got it right here. Point. Okay, here you go. And so this guy jumps in an elevator, stands on this guy. Hold on. See that guy weighs 200 units of something, maybe it's like 200 pounds, something like that. Right. He's just standing there. And then when the elevator starts to move, let's see, watch that needle. Bam. You guys see it jumps up to 220, like pounds or whatever, right? That tells you, because the fact that it jumped up tells you which way did that elevator start moving, up or down. Yeah, moving up, right? In fact, it's accelerating up right there. And then watch this after a little bit of time, right? But it's only there like a fraction of a second. And watch it, it immediately goes back to 200. So now is the elevator still moving up? Yes. Yes, it is. It's moving up how? Constant velocity. Yeah, moving up constant velocity. Right. Now, at some point, this guy's going to reach his destination floor, and the needle should jump down, I think. Let's see if it... Oh, yeah, you guys saw it jump down to like 180. Right? In fact, how much it deviates? Going from like 200 to 220 or 200 to 180. Do you think there's enough information there you can calculate the value of the acceleration? Probably do something like that. Okay. So that's going to bring us to elevator physics. Elevator physics, which is right here. Now, so you're in an elevator. Suppose you're standing on this bathroom scale. You have some regular weight, which is just mg. And if you're at rest, then shouldn't the normal force, the support force from the scale, just match your weight? So these two would be the same, right? But if you have upward acceleration, then the scale is actually pushing you up more than Earth's gravity is pulling you down. So overall, there's a net force up, and you'll accelerate up with the elevator, right? Guys, this derivation right here, you guys know this derivation, because this is going to come back, and AP could totally ask you to write this derivation as one of your FRQs, right? That would be completely fair. So Newton's second law of motion, sum of forces equals ma. In this case, the sum of forces is, well, normal force up minus the weight down. Wouldn't that be true? Right, so that is your net force. The difference between the two results in n times a. Is that okay? Newton's second law of motion. Right. Now, let's say we're solving for this normal force. Hey, you guys write this in your notes? You guys writing that in your notes? So, you guys good up to this line? I'm getting everything up to this line. So if AP asked you to write this, you guys could do this whole thing from scratch. Now let's solve for the normal force, which is the reading on the scale, which is what you just saw in the video. Can you add over the mg? Make it look like that, mg plus na. Right. Then, if you wanted to, could you factor out your own mass and do m times g plus a like that? Okay. Again, this is for an upward accelerating situation, which might be moving upward faster and faster. That's a more intuitive one. Or careful, it might be this. You might be moving down, slowing to a stop. That would be exactly the same scenario physically. Okay. Right. Same derivation, by the way. Right. Now, because what if you switch this to accelerating downward? What do you think would change here? Yeah, by the time you get to the end, right, it's just like you switch direction or something. Right. So here's all three main scenarios. So accelerating upward, you guys just saw that. If you accelerate downward, you do a similar process. The end result is this plus just changes to a minus. You guys that? Right. And while you're in equilibrium, it changes to tension in the elevator cable. It's the same. derivation basically, right? Okay. But just match the weight or the weight of the elevator or your weight. Okay. Right. All right. So, and the equilibrium case might be sitting at rest, or careful, it might be moving at constant velocity, and constant velocity might be up or down. And guys, if you're inside the elevator and you're moving up at constant velocity, or down at constant velocity, or you're just sitting at rest, do all those three situations feel exactly identical? Yes, they do. Yes, they do. Right. The only thing you can feel is a change in motion of the elevator, which is one of these. Right. You guys good with elevator physics? Good. All right. Right, so actually, this next one is basically the same thing. It's just a twist on this. Right? What if you tie these together with a string and you accelerate this either left or right? So if you pull this to the left faster, 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 doesn't this accelerate this up faster, faster, faster? Okay. And therefore, what happens to the tension in the string? It would increase. Right. Now, if you move this one to the left and slow it to a stop, isn't even though it's moving to the left, wouldn't that be like a rightward acceleration because it's slowed to a stop? Okay. Does that put a little slack in the string? Causes the ratings to decrease a little bit. Okay. Right. How about the other way? What if you move the top spring to the right, faster, faster, faster? Okay. In fact, an extreme version of that is you could hold it here, just let it go. You guys, if you just let it go, does the string go to like a slack with very, very small force just to kind of pull it along? And how about the other way? What if you're moving to the right and you just suddenly bring it to a stop? Wouldn't the force bring go up a little bit? Because it's like accelerating to the left. So you just want to stop. Okay. Friction. So what if you lift a weight versus drag it? So if I lift this, it looks like 10 newtons of force. But if I drag this across the paper, it takes, can that fit in the window? Just barely. It takes about three newtons of force to drag it at constant velocity. Okay. So I want you guys to try this with different weights. So let's say 10 kilograms, 20 kilograms, and 30 kilograms. Just make up some numbers. Okay. Let's say to lift it was, oh wait, I'm so sorry. So let's go 1.0, 2.0, 3.0. That's what I meant. 1 kg, 2 kg, 3 kg. Okay. The weights would be 10 newtons, 20 newtons, and 30 newtons to lift. Okay. But what about to drag? Now, I just did one of them with you. I said it takes about 3 newtons to drag it across this paper. This one, suppose you do this one, it's like this many newtons. Suppose you do this one, it's like this many newtons. Okay, I'm just making stuff up. You guys get the idea, right? Okay. Now, so in general, does it take usually more force to lift than drag it? Okay. Now, that's not necessarily like a law of nature. There are exceptions to that, but very rarely. So look at the ratio of the drag force compared to the lift force. Is that 3/10? And the 6/20, is that also 3/10? And 9/30, does that also reduce to 3/10? I guess it's like a consistent ratio. That'll be true as long as the materials are the same. So you got like bare metal against paper, something like that. You have to be careful. Some of these lab are like coated in paint, so it might change a little bit. Okay. But that's called the coefficient of friction. And I'll have you guys do a more extensive lab on that in the next couple weeks. All right. How about what if this is like? Let's see, my posters here. What if this is like swinging around? Okay. Compared to being at rest. So looks like a conical pendulum. Okay. Now, guys, this conical pendulum. Guys, everybody, go look up here. Go look up here. Okay. Guys, how many forces does this weight right here have on it? 2. It only has 2. Okay, so it's conical pendulum swinging around. Okay. It has Earth's gravity pulling straight down, so it's weight mg. Okay. And there's also a tension in the string called S of t. That's it. 2 forces. That's all. Now, you guys won't see this for a few weeks, but eventually, just set this up for now. Now, guys, which force is bigger, the weight down or the tension force up to the left? The tension, definitely. Because look at this. Could you break this into components and say, well, it's kind of pulling in, it's kind of pulling up at the same time? Components. Okay. And doesn't this upward component have to balance the weight pulling down? Yeah, it sure does. So vertically, this is not moving up or down. Okay. But horizontally, it is on a curved path horizontally, isn't it? Yeah. So there is actually a net force. This is not in equilibrium. There's a net force. Yes, and the tension is more than the weight in this case. So that would be like take this one right here. The tension is more than the weight. Okay. And then for buoyant force, this one we're gonna get to probably January, February timeframe. Okay, something like this. Suppose this 1 kilogram weighs 10 newtons. You dunk in the water. When the weight rating go down a little bit, okay. Suppose it goes down 7 newtons. Do you see have an overflow straw right here and then an overflow can? Okay. It turns out, and you guys will learn this again next semester, is that this upward buoyant force, this sort of helping it trying to make it float, right? So why you float in a pool is a buoyant force, right? Is exactly equal to the weight of the water displaced. So if you caught all this water and you weighed it, you see this 3 and the 7 add up to the original 10. Yeah. So it's called buoyant force. Okay. All right. So again, this was a really an exploratory lab. I just wanted to get you guys to get your hands on the spring scales and the weights and really test out all these ideas and see how all these ideas are working. And then we guys are solving puzzles down the road. Then a lot of this is going to lead right back to that lab. All right. Any questions on the spring scale lab? Hey, I got a mystery for you guys. Mystery. We got mystery cup. This looks like a fine cup right here, all hot glued together. Yeah. I would drink out of this. Oh wait, I think. What is this? Is there a hole in the bottom of my cup? What's on the other side? Oh, another hole in the bottom of the cup. So that's probably not very good. I don't know. Let's see. I'm gonna put some water in this. So I gotta do this off screen. I can't really move my camera so much. Okay, but I'll fill this halfway with water. Okay, and I'll just show you guys. So if you're watching this video, you have to sort of take my word for part of this. But you guys see how it's filled halfway with water? Halfway with water, right? And the water does hold in the cup. So it's something to do with like a straw hole, but I mean, it is functioning fine. There's no problem so far. Okay, but, all right, you guys ready for this? Watch this. I have to do this off screen. I'm going to fill this up to the brim with water. To the brim! And then, oh no! Water's leaking out the bottom. Oh no! Back in the day, this was back in ancient Greece that they used to have this, and so if you had a guest over, he's like, "Give me more wine." He's like, "Ha ha ha, I certainly." And he filled the cup to the brim. Oh no, I'm getting all wet. Oh no, so much water all over the place. Oh, make it stop. I can't make it stop. Oh no, my clothes are getting soaked. What do I do? It's like I've been swimming in the ocean. Oh, it's still, it won't stop still. They get so wet. I asked for way too much. Oh, I'm so greedy. Oh no, I've learned my lesson, my terrible ways. It still won't stop. Oh no. There's still more. And then finally, that was longer. All right, okay. This little dregs of water, but pretty much drained, didn't it? All right, there's a little tiny bit left. It also picks up a little bit. Yeah, pretty much drained. Pretty much drained. Okay, so. Question for you guys, and I want to give you guys a couple of days to think about this because some of you guys might know how this works, and some of you guys might want to think about this one because got a fun puzzle going on. Okay? Is what's going on inside this cup to make this happen? So I'll give you guys a recap right here, sort of a cross section. It's a scenario. Okay, so we've got some kind of hot glued together cup contraction. I look at the top and I see some straw hole here. I look at the bottom and I see some straw hole here. Okay. Now, I originally filled this with water, like halfway with water. And the water stayed in the cup perfectly fine. No problem. Water stayed in the cup. Functions perfectly fine as cup. Then I fill the cup to the brim and water starts flowing out the bottom. Oh no, I'm all wet. Okay. But this water level doesn't drain back to the halfway part where it was perfectly fine before. No, like the whole cup drains. And you guys get this little dregs of water, just like you guys just saw. Yeah. So I'm going to give you guys a day or two to think about that. Is what's going on inside the cup? What's going on with the straw, like the picture of the straw, and what physics principle would make that work with that technique? Right? So you guys be thinking about that. Okay. And you guys got your notes out, so we're gonna do some free body diagrams for the rest of class, go as far as we can, and then so one day at a time here. So go back to the beginning of the presentation. Join. All right, free body diagrams. Okay. So, here, free body diagram. Yeah, good. Okay. All right, so free body diagram. It's a diagram where we're going to label all the forces acting on an object. All right, now, there's little technical details. So there's something very, very similar called a force diagram. That's actually what that is. Now, especially for the next few months, we're just going to do it this way. So draw force vectors to represent the relative magnitude and direction of the forces. So guys, when I say relative magnitude, if you draw, because you guys know forces are vectors. So if you draw one arrow that was twice as long as another arrow, wouldn't that represent like effectively twice the force? Guess that, and also the direction, right? Because there's some direction associated. Okay. Guys, for AP, here's the important detail for AP. Always connect the tail of the vector to the center of mass and draw the vector extending away from the object. AP is really strict about this rule. Heard AP graders talk about this. They say, well, even if it's not connected by like 1 millimeter, they sometimes don't give you the point. So be really careful about that. Right? Again, the sort of exception to this sort of is several months from now, when we get to rotational dynamics, we might have to have different forces at different locations on an object. Right? But until we get there, always draw the forces acting at the center of mass of the object. Okay? Right? And then you guys know forces are measured in newtons. Okay? Guys, are velocity vectors force vectors? Is velocity a force? No. Is acceleration a force?
Yeah.
Also, no. Right, different concept with different units. Although forces do cause acceleration, so maybe it's a little closer tie-in. But you guys know forces are measured in newtons. Velocity is measured in meters per second. Acceleration is in meters per second squared. And on your free body diagrams, you only draw which one of those? Forces. Yeah, forces, which would be measured in newtons. Yeah. Guys, do velocity vectors show up on your free body diagrams? No, they do not. No. Okay. So let's do some examples. Block at rest on a table. Block at rest on a table. So there's your block, center mouse dot right there, boom. Okay. Could there be one force straight down? I call that weight. Okay. So you can call it mg, could be weight, or you can do F sub g, like force due to gravity. Okay, either one. Right, that right? Okay. Now, is that all, or is there more to that diagram? There's more. There's more. Especially if you see at rest. Guys, at rest, is that a type of equilibrium? Which means that all the forces must sum to 0. What force am I forgetting here? The normal force. Normal force. Aha. Okay, and those two actually do zero out, don't they? Okay. So they zero out because equilibrium. Anything in equilibrium. Guys, whenever an object is in equilibrium, all the forces have to zero out. Okay. How about block at rest on a table and we're pushing it horizontally, but with not enough force to overcome friction between the block and the surface? Okay. So do you think there's a weight and a normal force just like before? Right. And this time I'm pushing to the side a little bit. So push to the side. Okay. Now, is that the whole picture or is there more to that picture? Oh, wait, there's more. What am I forgetting on this one? Aha, friction. Aha. Okay. And, ooh, do you guys see how the friction exactly cancels out the pushing force or the applied force? Right. So got all those forces are labeled. Right. Those are common labels. Right. So mg or F sub g could be the weight. F sub n could be the normal force. Sometimes you see just plain capital N for normal force. I don't like to do that myself, but you might see that printed somewhere. Right? F push or F applied. A lot of subscripts you can put on that. And FFR is force due to friction. Okay? Right, so yeah, if it's at rest. And guys, would this be static or kinetic friction? Static, because we haven't overcome the initial friction yet. So actually, this frictional force would be changing depending on how hard you're pushing. So if you push with like 1 Newton of force, friction would also be 1 Newton. If you push with 2 Newtons of force, friction would be 2 Newtons. And it builds up like that all the way until it finally breaks friction and starts sliding. All right, let's do a block on a table. There's a block on a table. Push horizontally so that the block moves with constant velocity across the surface. I threw a velocity arrow to the side, but it's clearly not part of the free body diagram. It's just for context, right? Okay. So do you need an applied force pushing to the right? Boom. And you also need a what? Friction force to the left. Okay. But how should you draw the friction force? Should it be shorter than, longer than, or the same length as the pushing force? Guys, here's the giveaway. You guys see this term right here? Constant velocity? Constant velocity. Guys, constant velocity. What's the acceleration equal to? 0. Therefore, what's the net force equal to? 0. Would this block still be in equilibrium? It needs to be according to the setup, but does the diagram show equilibrium?
Yeah.
Not yet, but it only would if I make the friction force equal in magnitude to the pushing force. They're saying, right? Actually, is this free body diagram, does that look pretty well identical to the last slide where the block was just at rest? Yeah. If you did not know if that was static or kinetic friction, in this case it is kinetic friction because the block is sliding. Right? But if you didn't know, you just saw the diagram, you didn't know what kind of friction, you wouldn't know whether the block was moving or not. It'd be ambiguous, right? Maybe it's at rest or maybe it's constant velocity, but those have the same type looking free body diagram. Right, guys, it? All right. Block on a table, push horizontally so that there is a net force. Ooh. So let's put a weight on it. Let's put a normal force on it. Okay. And because if you want there to be a net force, could you just make the two horizontal forces different? Like maybe, for example, you're pushing more than the friction. Okay. No, guys, that block right there, could that block be going constant velocity? Huh? Who says no? Who says no? Yeah, there's my winners right there, my winners. Guys, why is this block definitely not constant velocity? Because there's a net force. There's a net force. It must be accelerating. Is that true? Takes over to Newton's second law of motion. Net force equals mass times acceleration. Okay? Guys, furthermore, this specific diagram, you can specifically know that it's what? Speeding up or slowing down. It must be doing what? Yeah, this one in particular has to be speeding up. And you know that. Here's why you know that. Because friction, guys, the direction of friction is always which way? Opposite of the velocity. Right? It's like trying to slow it down, sort of. So if that's true, then this block must have a rightward velocity. And I also see a rightward net force, which means rightward acceleration, which means that velocity and acceleration are both to the right. So I know this block is specifically speeding up. Okay. All right. Let's do rocket and free fall. Now, free fall also implies no air resistance, no air drag. Oops, whoops. Guys, are there any other forces, or is that the whole thing? Well, no air drag. Right. That's the whole thing, right? Guys, you drop a ball off a cliff. Isn't that the whole free body diagram? Guys, what about this? What if you throw a projectile in the air? What about your, you guys remember blasting those bouncy balls off the balcony? Right. Let's say after the blast happens and it's just in free fall and it's just on that parabola path and it's falling. Guys, that bouncy ball on a parabola path falling, would that be the exact free body diagram right there? Moving to the side? Yes, it would. Yes, it would. Actually, that there, you do not know the direction of motion. Is it going up? Is it going straight down? Is it going to the side? Is it going on an angle? You have no idea from the free body diagram. Yeah.
Wouldn't there be two force vector on the constant ball?
Guys, is velocity a force? Yeah, velocity is not a force, right? Right. So yeah. So just a push or pull. Anything is being pushed or pulled. What if there is air drag before terminal velocity? Let's say it's falling straight down. Guys, if it's falling straight down, would you draw that air drag opposing the motion like that?
Yeah.
Okay. Let's do terminal velocity. Guys, could the air drag build up so much that the air drag exactly cancels out the weight? Something like that? Right. And that would be terminal velocity, wouldn't it? So then at that point it could go down to constant velocity. Right. Let me get lights here. Here's lights. So we'll hit a pause point right here. All right, we'll pick up here tomorrow. One more detail on that one right there. Since we're looking there, I got for you guys. This question came up earlier. How much drag force? Drag force is proportional to v squared. So just FYI, good enough. Good thanks. All right, that's our real pause point.